Welcome everybody to this program on self-learning AI systems. It's called Can We Trust Self-Learning AI? It's a program by Radboud Reflects in collaboration with the Donders Institute for Brain Cognition and Behavior. So many decisions in our lives today are not taken by ourselves, but are taken by artificially intelligent machines, by computers. So whether or not a skin rash is actually just a skin rash, or it might actually be something like skin cancer. There are really, really interesting and well-developed tools, AI tools, that can tell us that sort of thing. But it's also used, self-learning AI is also used for determining whether or not people can get a mortgage, or whether a certain combination of personal characteristics makes somebody a likely terrorist. So really, really important life decisions are taken by computers, by artificial intelligence. And the question that we'll be concerned with today is, well, can we trust those decisions? And most of the time, Pim Haselager of the Donders Institute will at least try to give an answer to this question. The evening is set up as follows. I'll start with a very, very brief introduction on the whole idea of self-learning AI, and then Pim will take over and do the real stuff and he does the difficult stuff because he's the expert. Then we'll have approximately 20 minutes, 25 minutes of discussion, and then the audience at home and the audience in the room here can ask questions. And we have divided it in two sections, so the people at home can ask questions first. They can do this with Mentimeter. There is a code that you have to fill in, but I don't know what the code is, but if you're at home, it's shown at the bottom of your screen, I am told, hopefully now. And then after, we'll try to at least reserve like 10 minutes for the audience here, the live audience here. And those are just questions. You can just raise your hand, and then we'll pass you a microphone, and we can continue the discussion. So, my bit, so to speak, my bit is really small. It's like a 10-minute bit, and I'll try to explain why the whole notion of trusting AI, why it's an issue. And what I'll try to explain is that the big issue is that in order to determine whether or not you can trust AI, you need to understand what AI is doing. You need to understand that the kind of decisions that are made by a computer, that the decisions are based on reasons, and that the computer can explain to us what those reasons are. What I would like to at least try to argue in 10 minutes, maybe 15, is that it's that with the kinds of self-learning AI that are sort of pervasive today, that it's quite impossible to understand why certain decisions are made by computers. Or, in other words, I would like to explain how it can be the case that we can build machines that can make decisions for us, or can make complicated reasonings for us, and we make the machines, but we don't understand what the machine is doing. And most people think that's ridiculous, because we are the ones that make the machines. So how can it be that we make machines that can do stuff that we don't understand? How can we build things that we don't understand? That's what I'm trying to explain. I'll be trying to explain this with a very, very simple example. It's sort of a real-life example. It's not a really real-life example, but it's an example of a very old research. It's 1978, so it's really old research, when people first started to use these so-called neural networks, which is the kind of AI that we'll be talking about. So this is a hypothetical problem. Suppose there is a harbor, and in the harbor there are rocks at the sea bottom, but there are also mines that are sort of, say, they're the remainder of the Second World War. It's a harbor in Hawaii, for instance, and there were mines placed by the American Navy in order to deter the Japanese, say. Now, the mines are still there, and you want to get rid of the mines. How do you detect the mines? Well, you can use a submarine with sonar. And sonar basically is you send out a certain noise signal, and the reflection of the signal bounces back, and you hope that there is a certain fingerprint that you can find in the sound that returns from either a rock or a mine, and that you can use the fingerprint so as to say, okay, well, that might be a rock and this is a mine. So what you can see here is that that's a sort of frequency range. There are there's low sounds, there's low frequencies, there's high frequencies, and everything in between that is being sent out by the sonar of the submarine. And also, I mean, and the sound that bounces back has a certain signature, if you like. There's in this case, there's a lot of mid frequencies. There's very few low frequencies and not a lot of high frequencies. But this is the kind of sound that bounces back. Now you want to be able to tell from this kind of graph, is this a rock or is it a mine? Turns out, and this is real life, it turns out you can't. People cannot tell from this kind of frequency range that bounces back whether the sound bounces back from a mine or a rock. So then, what do you do? And this is, in a certain sense, this is real life research. This is a laboratory situation in which they have actually mimicked this, but they did this. And what they did is they wanted to develop a very, very simple neural network that can actually do what humans cannot do, namely determine from the sound that bounces back, that is a rock and that is a mine. So first, something about a very, very simple, and I'm sure that Pim is going to give you a more detailed picture, and actually he's going to give you sound as well. Spoiler alert, sorry. So this is a neuron, two neurons actually. It's a neuronal cell. If a cell fires, that means that there is a certain electric current or that is made by the body of the cell. It travels along an axon to, I'll simplify, to the next cell. If there is enough electricity, so to speak, then the next cell will fire as well. You can sort of make a computer version of this by making an artificial neuron, which is called a node, that when it is excited enough, when there is enough activation in the first neuron, this is the activation. Activation in this case is just basically a number, and the number is between 0 and 1. And if there is some activation in the first artificial neuron and it's connected to the second artificial neuron, then it might actually induce the second neuron to fire as well, but depending on what is called the weight of the connection. So the weight of the connection is the extent to which the activation in the first neuron determines whether or not what the activation in the second neuron will be. Now, it turns out that the second neuron is also connected to a lot of other neurons, but this is sort of the basic, this is the building blocks of what we're going to work with. I hope you're still with me. I think it's kind of important to explain this sort of stuff, because then you really get why it is that people can build machines that do things that we don't understand. Okay, so these are the building blocks. And then you build something like this. This is a 3-layer neural network, and every one of those little balls is an artificial neuron, and they're connected in the kinds of ways that I've just tried to outline. But what we do now is that we connect the first, sort of the left-hand 13 neurons to the frequencies that bounces back from either rocks or mines. Yeah? So if there is a lot of mid-frequency, my glasses are not good enough, but I see that somewhere in the mid-frequencies there is quite a lot more activation in the different nodes than in either the bottom or the top neurons. And this is because there's more mid-frequencies than low and high frequencies. Yeah? So you translate the frequencies to these 13 neurons. And then you connect the neurons to 7 neurons in a sort of middle layer, and you connect the middle layer to 2 output neurons, and you call one rock and you call the other mine, just randomly. This sounds ridiculous. It is ridiculous, but wait. And then you assign all the connections between all these neurons random weights. You start with a completely random distribution because you haven't got a clue which of the frequency ranges signifies a mine and which of them signifies a rock. So you just start with a random distribution and then you let it run, and then usually say that the frequency is, in this case, comes from a mine, and you get this type of result. There's a sort of 0.52 chance that it's a mine, but there's a 0.48 chance that it's a rock. So this really doesn't tell you anything. And here comes the trick. Then you use a rule, a sort of mathematical rule, and that's the complicated stuff that Pim knows way better than I do. I really don't know. I mean, I'm pretending as if I sort of understand what's going on, and I sort of do, but not really. Because this is the stuff that I don't get. Apparently, people are able to use a mathematical rule called the generalized delta rule, which is sort of able to determine which of the weights that was randomly assigned is responsible for the false outcome. Yeah, so you use another computer, and the other computer knows that there is a mine, that the mine was the input, knows that the output really doesn't tell us much, and then figures out which of the weights is probably, but only probably, responsible for the false output. And then you start tweaking the weights. And this is the tweaking of the weights. That is the big trick. That's where everything happens. So you use the rule to say, okay, it's a mine. There was a 0.52 chance that actually that says the neural network that this frequency range was produced by a mine. Well, then we need to tweak a lot of weights, and then probably we get a little bit, a slightly better result. Suppose that happens. Suppose you get, I'm not sure if suppose you get this, like 0.56 after the tweaking and 0.44. Suppose that happens. Then you're sort of on the right way, but you're not there yet. And this is where the self-learning comes in. You use a computer that presents the machine with samples of mines and rocks, different samples. And you use the same rule, this is called backpropagation, to tweak the weights until there is a distribution of weights that gets you something like, like this. Like, I don't know what, like a 0.98 for a rock when there is actually a rock presented to the machine. So what happens? This is sort of the crucial bit. It's the tweaking of the weights according to a very complicated rule, while the machine or the neural network is presented with samples of mines and rocks. And as it turns out, this works. You get a machine. This is a real-life example. You get a machine that is able to tell us with almost certainty, like 0.98. certainty that is a mine and that is a rock. This has been done, and I think they only used something like 120 iterations, so 120 samples that were actually given to the machine, and then the tweaking went on. That process is called self-learning. It's not really self-learning because you need another computer that teaches or that presents the samples to the neural network and that does the tweaking. But there is no human involved. No human does the tweaking. The tweaking of the weights is something that another computer does. And you end up with a network that has apparently a certain distribution of weights and that is able to do something that we were not able to do, namely tell that is a rock and that is a mine. So I hope that this example sort of gets the point across that it really is possible to build machines that do something that we don't understand. Because if you ask the machine, look, what you just said there's a mine, and it probably is a mine because we now know that you can do this, but why do you think it's a mine? The machine can't answer. And then you open it up and you try to figure out how the machine does it, and all you get is a distribution of weights. That's all the answers you get. And that's not enough, because you don't know why that distribution corresponds to a mine or a rock. That's the problem of explainable AI and self-learning AI. So we can build machines that can do stuff that we don't understand. And today, these machines make incredibly important decisions for us, like, do you get a mortgage? Or are you a terrorist? Or is this skin cancer? That's the problem that we'll be discussing further. Now with Professor Pim Haselager, who is Professor of Societal Implications of Artificial Intelligence and Cognitive Neuroscience, but we'll not be talking about cognitive neuroscience, probably, who knows. But the topic today is artificial intelligence, so Pim is going to take it from here.
Thank you. Well, in a way, there's nothing left for me to explain, of course. This was all crystal clear, right? That's how these things work. And it's nice, I'm clicking till I get my own slide, it's nice to see that this is stuff that was built in the 80s. Neural networks really started that approach, I will say a little bit more about that in a second, started becoming popular in the 80s. And in that period, we could work with simple problems like the mine rock, still highly stylized and simplified, but it was working with features that were completely new and that were actually interesting because they were neurally inspired. They're called neural networks for a reason. And so people started thinking, hey, that's nice. By learning about the brain, we can then maybe also improve AI. And by improving AI, maybe we can understand better how the brain works. That's very nice. You can do both at the same time. At the same time, like the backpropagation that Mark explained, there were limits to what you could do. And somewhere along the 90s and the zeros, certain principal problems were solved with delta rules. It's all highly mathematical. We're not going to go there. This was a lot of mathematics, I thought, already. But a second point that was crucial to the real-time, real-life applications of neural networks was simply computer speed. The calculations, if you go through a network like that, take a long time. You really had, with those old machines, to wait. Moreover, you had to get numerical values, basically the numbers that Mark showed you, in order to get the network to work. You couldn't give it raw data. You couldn't play it as sound and then it would derive the numbers from that. No, you had to sort of inform it about what the numbers were. Those days are gone. Computers are now so powerful and the technology is so advanced that you can simply give it, for instance, sound patterns. Just you play the sound and the machine will take in the numerical value by itself. Or you play it a video and the pixels on the screen, you know, the one-in-one light points that you see on a television screen from left to right and from top to bottom, will be automatically translated by the machine itself in real time. It goes extremely fast. And we thank this in large part to progress in graphical processing units and other developments. So it's more powerful, it's more speedy, it can work with real-life data, straight from the camera, straight from the microphone into the neural network, and it works. Well, how does it work? Again, we have natural neural networks, brains. And what I find exhilarating, what I find really beautiful about artificial neural networks is that they help me to understand my own brain. And yours, by the way. So that's cool. But it's worthwhile figuring out, so here you see a neuron on the left. Here you see the major pathways on the right that are transforming all that information that Mark talked about way and backwards in various directions. There's really highways in the brain where a lot of information travels from one location to the other. But if you listen to the sound of one neuron, you can connect them to a speaker, and you get the sound, you hear the actual information that the neuronal signal is progressing. And that sounds more or less like this. The sound technicians, when we rehearsed this, thought there was something wrong with the equipment. But for me, this is one of the most beautiful sounds I know. And it's really true, because this is the mystery of the neural code. This is how we think. This is what happens now in all our brains. Of course, it's soundless because they're fortunately not connected to speakers, but this is the information that transfers from one neuron to the other. We have 10 to the 11th neurons, that's a lot. There's enormous amounts of connections, and all this is going on with that particular sound. Can I just make you listen again, if that's possible? This is you. This is your thinking. This is your thoughts. This is your feelings. This is your hopes, your dreams, and everything else. It's incredible, no? I find this so beautiful. So the question is, well, what does that mean? Yeah, we don't know. But we would like to know, to a certain extent. Maybe we can, in the discussion, also discuss a little bit why we wouldn't want to know. But neural networks use that same pattern, and so maybe they can help us a little bit. So it's worthwhile trying to figure out how they work, how that sound that you heard, that activation code of the neuron, that firing frequency basically, provides or represents information. That's a crucial question, not just because we want to know how machines make decisions about everyday life. They also work for Tinder, by the way, for anyone interested in that kind of stuff. So the dating candidates that you get, there's a learning neural network there underneath that gives you your new dating partners. And so they're inspired by neurons. And here you see cortex on the left below. And their neurons are more or less organized in columnar structures, like a sort of building block consisting of 5 layers. And it's never going to be more than 5 layers for a very simple reason, because the skull has a certain kind of shape and a certain kind of volume that doesn't really grow over time. And this is because when kids get born, there is a limitation to the birth canal that doesn't allow heads to be bigger, and there's only so much growth that a head can have during a lifetime. So we are stuck as a biological species with 5 layers of neurons in our neocortex. That's a lot of stuff that we can do with that kind of neurons. At the same time, it's an upper limit for purely biological reasons. You see sometimes these science fiction movies where the artificially advanced species has this cone kind of structure in their skull. That's one way to get more volume in and still be born in the natural way. That's where that comes from. But of course, artificial machines don't have that limitation. There's no need to stick to 5. There can be 500. There can be 5,000. There can be 500,000. The sky literally is the limit. So just in terms of computational resources, artificial neural networks can outweigh whatever we have that we carry with us. So that's one reason why we can do things with AI neural networks that we cannot do with biological ones. And so you see here a pathway, for instance, from the retina with light-sensitive cells that's going to a middle nuclear structure, the lateralis geniculatus nucleus, then it goes to the visual cortex, then it goes up to the motor cortex, and it provides information about where in the visual field the stimulus was. And here it goes ventrally to a language-related centrum that makes you identify the object that you saw. Oh, it's a book, or it's a mine, or something like that. And you can basically rebuild that information in a more linear fashion that you see here at the lower right corner, and that's your artificial neural network. And again, the amount of resources that you have is practically unlimited. So we really have now monster calculating machines that do a lot of that work. Now the question is, what are the neurons in the middle of such a network? You see there hidden layer 1, hidden layer 2, hidden layer 3. What do they represent? What kind of knowledge is there? They make that funny noise that you heard 2 times. What does that mean? Can we get access to how that information is represented? Well, you can think of it in the following way. If you take a neural network with a layer of 3 neurons, you can identify or represent the activity from 0 to 1 as a line. You know, you have an x-axis, a y-axis, and a z-axis. You see that here. You can basically get a cube. I'm going to walk here. I need a stick at some point. I'm told that people at home cannot see the pointer, so I'm trying to both tell you and tell them where I am. So think, for instance, of faces that are being recognized by a neural network. Okay, one identifying feature could be eye separation. You see that on the axis going from left to right there. So an activity of 0, no sound, no activity of the neuron, would represent that the eyes are very close to one another. A maximum activity, full blast in the speakers, would mean that the eyes are far apart. You can do the same for mouth fullness or for nose width and lots of other features. I only showed 3 here because on a 2-dimensional space, a page, you can show 3 dimensions but not more. But mathematically, it doesn't matter whether you have 3 dimensions of 300 or 3,000 or 300,000. The principle is the same. So the activity that represents a face basically consists here of 3 neurons that make that sound together. It's 3 times the noise you heard earlier. But you can also imagine that at some point it becomes 300,000. It's a lot of noise, and that's what makes it so difficult for us to decipher. Is that problem kind of clear? This is how networks represent knowledge. Then you can identify regions in that space where, for instance, there is a male subregion or a female subregion, a very big region which is indeterminate and in principle not desirable to ask about. That's a 21st century kind of development. And there's much more that you can represent in that way. But this is how we think about knowledge representation in neural networks. Now the next question. So we saw a simplified example with 3 neurons, and we could more or less identify what it means. I simply postulated, okay, so this is about eye width, you know, the distance between the eyes that this neuron represents. 0 is this, 1 is that. But now we look at real neural networks that do face recognition. You see the faces on the left, all kinds of pictures, and over there on the right, the output layer, you see, for instance, the identification of a male or a female face, or an old or a young face, whatever you prefer. Is that kind of clear? You train these networks, there's backpropagation, so they learn automatically to address the weight setting so that the answers are more or less correct for a maximum number of possibilities. And then you start asking the question, so but what do neurons in, for instance, hidden layer 1 actually represent? Or what do they represent at the end of the input layer? Here you kind of know by the output layer. There it's clear, it's a male face or a female face or an old face or a young face. That is sort of identifiable. But in the middle, it's really hard. And then if you start looking on the basis of visual input, what you see, and I will zoom in on this later, so don't worry if you don't see it immediately, is a sort of line detection maybe, which is nice because you need to see the contours of a face, for instance. So we first go almost like for drawings. You know, the visual system first starts identifying the outline of the skull, for instance, and the location of the eyes, these 2 patterns with the nose, mouth identification. So line detection is very important. Then in the middle, it's not so clear what you're seeing, actually. Maybe you see an eye here and there, but there are many representations in terms of pictures that we cannot identify. They don't make much sense. Let me zoom in. So this is an example of a car. You have the line detection. That's, you see the car on the left, then lines, more or less, black-white transitions. Then you get stuff that is really difficult to see. Some things I think I see something like a wheel here and there. Maybe you see that too. But very many other of these representations I don't know how to interpret. I don't know what it means. Actually, when I look at them, I always think I need glasses, and then I put my glasses on and I think I need better glasses because I cannot really see what it is. That's the problem, the knowledge representation problem. Here I zoomed in even more. What does this mean? What kind of knowledge is in that network? Apparently the network has learned that this kind of information here in the middle is crucial to identifying cars, or distinguishing male from female faces, or old from young faces, or whatever kind of distinction you want the network to make, pines and rocks. We can try to see, to reconstruct what is happening inside there, but we cannot really make much sense of it, except for some cases. And the funny thing is, and that's another reason why it's cause for enthusiasm, that we have the same problem with brains. It's relatively easy to trace the information transfer from the retina into the visual cortex, then going up towards the motor cortex for localization or going down for labeling, let's say. But after that, when it goes prefrontally, where you basically are thought to make decisions, to make plans, think of alternatives, etc., we lose the flow of information. We no longer know what exactly is represented. We can look at brain activity, but it becomes meaningless in a similar way to how knowledge is represented in these neural networks. We lose track. Then when you get closer to the motor cortex, when you go to output, whether it's for voice, you want to say something or do something with your arms or hands or with your legs, we start recognizing it again, exactly like in these artificial neural networks. There's plenty of differences between real biological networks and artificial ones, but these similarities are interesting. They're also frustrating because it's clear that we don't know certain things, but yeah, it's the same as with the brain. So somehow we need to crack something in addition. Good. More examples of the same. Here's, for instance, elephants. So we have faces on the left, cars, then elephants, then chairs. If you look at the hidden layer pattern of the elephants, the one in the middle, you really don't see anything. The information is there. It's represented somehow in this weird neuronal code that you heard at the beginning, but we cannot interpret it. That's the problem of not understanding how neural networks work. That we can look at it, we can analyze it mathematically, but we don't know what it means. It's as incomprehensible as that weird sound of the beginning. You can add color. This is for a fish recognition. And although I find them beautiful, they don't mean anything. That's the problem. So in terms of efficiency, the accuracy of the predictions, the learning capacity, neural networks are brilliant. They're fascinating. They're the best tools we currently have to learn new skills. In terms of explainability, they're terrible. They're the worst we have. So it's hugely capable and incomprehensible. That's a problem. That's a problem for AI. It's a problem for neuroscience, because we don't understand our own brains. But it's also a problem for society. Because we're having these machines making decisions, as Mark said, and we don't really know how they do it. So how sure can we be that they're correct? Or who or what do we blame if something goes wrong? Huge issues in society. And a label that I want to introduce to you, maybe you heard it before, but it's not very often mentioned, is algocracy. You know, democracy, demos, the people rule. Algocracy, algorithms rule. We are having more and more of crucial infrastructure of human society being run by algorithms, and that could be a serious problem. So just this quote from the same paper by John Danaher, a very readable paper, I can recommend it. One of the most noticeable trends in recent years has been the increasing reliance of public decision-making processes, bureaucratic, legislative, legal, on algorithms. The rise of such algorithmic governance creates problems for the moral or political legitimacy of our public decision-making process. This is real. This is what is happening now. And if you look at this problem in a little bit more detail, then you have two related problems. One is the hiddenness of the data. We have now huge databases. Basically everything that you're doing on your smartphone, on the internet, if you have a smart electricity or gas meter at home, all this information gets collected, what you buy with your Albert Heijn client card, etc. All this gets collected, which calls you make on your health insurance. I always tell my students, what do you think that health insurances do? They check what you buy for beer and deep freeze pizza in the supermarket, and they check your complaints about stomach aches with the doctor. And they see the connection. That's how it works. So all that is there, but we don't have access to those databases. So that's hidden. That's a big legitimacy problem. What data do they have about us? And they could be insurance companies or Tinder or Facebook. You don't want to know what Facebook knows about you. And for what do they use it? And even if we would get access, which normally is not granted because it's private property, you know, it's the ownership by the big company, etc. But even if we would have access, it would be too much for us to make sense of. You need artificial neural networks to make sense of all that data. So that's a big problem. Then the second problem is the opacity. It's a lack of transparency, basically. You cannot see through it. You can see the neural networks making their decisions, but as I just tried to show you, you cannot see what is being represented in the middle and how they come from their input to their output. So you're two unknowns that basically make fundamental decisions about society. That is a serious problem. So what to do? Well, this problem has been discovered, realized, and action has been taken care of a little while ago, say 10 years more or less. Took quite a while before this was affected in certain legal procedures, but we currently have a requirement for human intervention. So this is the Dutch government that in 2016 already formulated, knowing what was happening at the European Union level, of course, that in the end, always a human had to make the ultimate decision. Automatic decision-making with legal or otherwise significant consequences is not allowed. It should never be the case that a machine and only a machine makes the final decision. Sounds very reasonable, I would think. The famous, or rather the infamous GDPR, General Data Protection Regulation, in the Netherlands it's called the AVG. Maybe that rings more of a bell with some people. In Article 22, very famous article, the data subject, that's human beings, shall have the right not to be subject to a decision based solely, only on automated processing. Always there should be a human in the loop. Okay, good idea. So what do we get? We get now the following kind of system. There's basically data, for instance, about health, that gets translated by, for instance, a deep learning neural network of the kind that I already showed, into a recommended diagnosis. It's the medical expert system, the medical deep learning system, that says, well, given all that I get from the data that's being recorded of this particular patient, I think the illness is this or that. But that's not the end of the story, because there's a human on the loop that then says, okay, I will accept this hypothesis, this diagnosis, or I will reject it in favor of another one. So ultimately, when something goes wrong, there's never a responsibility gap or anything. It's the human doctor that makes the final decision. So this is a human on the loop. And in theory, there are several options, and I want to go through them to sketch the problem a little bit in more detail. So the first one was the traditional one. The human is really in the loop. So I get the information about the patient. I'm not a doctor. Don't rely on me, but I will pretend to be one just for the sake of the argument. I get the information about the patient, and I think, just like a general practitioner does, you know, the huisarts, okay, maybe it's you have the flu, COVID-19. Well, let's not go there. Human in the loop, all right? Then you have the human on the loop. There's a system, an AI system, learned the tricks of the trade, gets the information, comes up with a hypothesis or a diagnosis, and I, as a doctor, have the choice to accept it or reject it. That's the human on the loop. Then there's the human out of the loop, and this is currently being debated, for instance, in relation to killer drones. You know, these automatic airplanes that can shoot people, drop bombs, etc. The main argument here to have humans out of the loop completely is that the interaction between these drones can become so fast that humans are simply too slow to have a meaningful intervention. There's, of course, a huge debate now on banning that kind of technology because, yeah, not everyone, fortunately, wants these machines to kill automatically. But we know about bans in relation to military equipment, that's going to be an uphill struggle. So that's a current debate that's really going on. I'm just mentioning it here to illustrate the human out of the loop. But go back to the human on the loop. So I'm this doctor, and I'm getting this diagnosis of a system. That's the best that AI can provide. And I've worked with it, and it seems to work quite well for, I don't know, 100 patients or 1,000 patients. What am I going to do the 150th time? Am I going to think, well, I'm going to really think for myself and check very thoroughly, or am I going to rely on the system? In other words, we may be saying that the human is on the loop, but you actually might end up with the human being under the loop. And we see this already in self-driving cars. There's increasingly self-driving cars. They're not fully self-driving, lots of reasons for that. It's a whole different ballgame. But what we see is that people are supposed to have their hands on the wheel and look at the road in a self-driving car. What do you think people start doing after 10 kilometers or so? They take their smartphone, yeah, exactly, and they start doing other things. It's a bloody self-driving car. So how sure can we be that professional experts will be non-human in that regard? They know a lot more, that's why they're professionals, and they have a certain responsibility, so they will hold out longer. But will they always have the same attention and the same concentration as if they know that it's really depending on them and not on the machine? I doubt it. I think that a lot of professionals, and I give regular talks to those kind of groups in medicine, but also in legal professions, etc., are going to end up under the loop. And they will be a kind of moral crumple zones, scapegoats, if you like. You know, like with cars, if they have a crash, there's this area that you can safely sort of damage and the person inside still stays safe. Well, professionals using these kind of deep learning systems will have the same kind of effect, basically. They're there to take the blame if something goes wrong. They're filling the responsibility gap at their own expense. A difficult problem that we're working on. So you see in a lot of codes now that the suggestion is that AI has to be transparent. It's not enough to have a human in the loop. The AI has to be explainable. A human user should be able to see not only what recommendation the system makes, but also how it got there. And so, AI is in that sense nice, that it creates problems that it then requires itself to solve. It's a way of keeping your work, if you get what I'm saying. We create problems with our technology, but maybe we can use AI also to solve the problem, or at least to make it less serious, more understandable in a way. So this is called explainable AI, XAI. This is a huge research field currently. It's fast growing, and the problems are enormous. So I am not going to say that we know for certain that all the problems will be solved. We don't know. And maybe we can come back into discussion about, okay, so what should we do in the meantime? I'm now trying to sketch how we are suggesting to solve this problem. First of all, we have to notice that explainable AI is really complicated. It's not a simple problem. It has many aspects. For instance, you have different types of users. You have the experts, my colleagues who do real machine learning and deep learning algorithms. They talk in mathematical formula that I don't understand at a certain point. So they want different kinds of explanations. They need different types of information to understand what goes right and what goes wrong in the machines they make. But for a simple user who just wants to know, gee, was it the fact that I have red hair or not that made me get a mortgage or not? Or, well, you can think of more serious examples where stereotypes play sometimes a huge societal role. You know, they need an explanation at a totally different kind of level. Explanations have certain criteria. This comes from philosophy of science that you need to understand in order to have a system that generates an explanation. There's, of course, the laws and the regulations that have certain requirements that you need to formulate and specify so that the machine lives up to the legal requirements. And, of course, you have to have a lot of knowledge about algorithms. So this is not a solution, this is a field of research. You see the problem? So there's many people now working on this, but this is going to take quite some time before we actually have a lot of success. But I want to show you, and then I'm done, a little illustration of how one method, for instance, works. Again, related to visual information recognition, because that's easiest for us to understand. But the mathematical principles apply to all kinds of different domains. So it's just to give you an idea. First, you want something that's called a heat map. You see in the middle with the dog. That's basically the part of the input space. You remember what Mark showed you at the beginning, that there's all this data from the echo that was being recorded over the input units. So you start trying to identify which input parts were most crucial to the outcome of the network. And you can do that, I will show that in the next slide, but bear with me for a second. So once you have the heat map, you can say, okay, we understand a little bit what it was about the input that was crucial. And then we can look further down in the network in order to see what was it about that information representation. The same goes for language. This movie was very good. Is that a positive or a negative sentence? It's positive. Where does the positivity come from, so to speak? Well, most likely from the last word. If it would have said the movie was terrible, everything else was identical except for the last word, and then it would have changed to negative. So that's how you can see which parts of the input space actually help you. Then you can distort the image deliberately. So this is the recognition of a particular type of bird, the hummingbird. So this is the unobstructed picture. You don't damage the picture, so to speak, and you see that the network gives you a high confidence estimate. It's a hummingbird with a 93% certainty. Great. Then you delete the head section of the picture. And suddenly you see that the hummingbird certainty of the neural network actually goes down to almost half. So that's a huge loss. Apparently, those pixels right here with the face of the bird carry a lot of relevant information to the network. Good. You check other parts, and you see that there's damage done, but not as much. So you create a heat map, which you see below, the blue one, and with a color intensity code, you can say, okay, it's these parts that actually play the largest role in the decision of the neural network. So as you will damaging the network, or the input of the network, you get a better understanding of what happens. And you can also do this with artificial neurons. Of course, you cannot do lesions in a real human brain. That would be highly immoral, although it has happened in the past. But you can make lesions in an artificial neural network. There's no suffering involved there. So you can actually take out certain parts of the network and see how that changes the information processing of the network. And that makes you understand better how it actually produces the end result. Is that kind of clear? I hope it is, because the story is finished here. We can go to the discussions. Deep learning neural networks, very powerful, but extremely non-transparent. Effective human oversight is required in the European Union, but to be perfectly honest, I doubt that that's really going to solve the problem. That's a legal solution that's psychologically not plausible, so to speak. You cannot rely on people actually doing what they should be doing in those kind of situations. So the best hope we currently have is explainable AI, where we use AI techniques in order to address the problem that AI itself created. Thank you. Oh, yes.
Yes. All right, we've got lots of time. Thank you very much. So, first question. To what extent can we trust AI? Because we've spoken a lot about understanding and explaining AI, but to what extent can we trust it?
Well, I would be inclined to say that we can trust AI to the extent that we understand it. And if we cannot explain it, I wouldn't trust it.
Okay, so explainability is for 100% a precondition for...
Yeah, whether it's sufficient, I don't know, but necessary in any case, yeah.
Right, because I was thinking of say neural networks that are able to determine whether or not a skin rash is indicative of upcoming skin cancer. Suppose you have a machine that really does not make. I mean, the example you gave of the GP, like you have 1,000 patients, and this neural networks always gives.
But there's no guarantee for always. That's the problem. If you don't know how it works, it can go right for thousands of times, and then suddenly it can go wrong. You need to understand the inner workings of a machine in order to be absolutely sure under what conditions it will function correctly, and under which conditions it might actually not, or for how long it might work, or for what kind of data it might work, or for what kind of problems it might work. Without understanding how the machine actually works in full detail, in terms of explanation of not only what it comes up with, but also how it comes up with, there's a crucial element lacking. And you could argue legally, I'm not a legal expert, but I hear from some of my colleagues that using such machines could border on being reckless or negligent, which are legal terms I understood for culpability. If you take risks in certain decision making by using a technology that you don't fully understand, there might be problems there.
But don't you need an alternative? I mean, so suppose you have this machine and it's right almost all of the times.
Yeah.
Sometimes it misses, and then you would say, I can only trust this machine to the extent that I can explain it. I can't explain it, so I can't trust it. But if we have no alternative, if the doctor would not be able to say, I don't know if that's a rash or a skin cancer, then what?
No, I understand what you mean. So you have here a few options. First, like with self-driving cars, people say, look, maybe it makes mistakes, but it will make less mistakes than human beings, human drivers. So there will actually be progress if we use self-driving cars, even if we wouldn't always understand why it makes the decision that it makes. And even if we accept that sometimes things go wrong, the damage overall will be less. You can argue that way, and there's certainly something to be said for that. On the other hand, I always think that it seems fair to ask more guarantees in relation to technology than we ask of human beings. We know human beings are fallible. When you're driving, something happens, you have an intuition kind of response, a fast, maybe panicky kind of response. That's what we are, what we can do. We have to accept human fallibility simply because we are humans and fallible. But machines, I wouldn't like a bridge, even though maybe it's safer than being carried across by someone in a boat, I wouldn't like a bridge that isn't testable and explainable in terms of the weight that it can carry. We are used to setting higher demands on technology than on human beings.
Right. But now you're going somewhere where I was also planning on going in our discussion. No, I mean, so you compared artificial neural networks with real neural networks, i.e. brains. Brains are not that reliable. You basically just said that we set higher standards for technology. But what kinds of explanation would we like to have in order for us to be able to say now for all that we know we can really trust this network?
Well, that's a good question, and I think it depends on the context and the users. Like I already said, explainable AI is a very complicated kind of domain, so it's not just one factor. But depending on what is at stake and for whom something is at stake, you can set different criteria. And one of the tasks of explainable AI is figuring out under what circumstances something needs to be explained in more or lesser detail. And of course, what you say is true. You can ask a doctor or a judge or a chess player. I play a lot of chess. Why do you think that this is a good move? Or why do you think that this patient, you point to certain features and then you say, but why, how did you think of that diagnosis or that evaluation? I don't know. It just pops in my head. I have the experience, I have the training, and that's how I think. Yeah, but how do you think? I don't know how my neurons work.
Okay.
I'm not a neuroscientist. So you see that also in human explanations, there's an end of the line, so to speak. At some point, the explanations stop. And then you can say, well, if that's the case with humans, then why not simply accept that with technology it does so too? Well, precisely because it's technology. Because we can ask those questions. We can do the lesion studies. You know, so technology gives us the chance not only to discover the problem, but also use the technology to find answers at a deeper level than maybe currently we are capable with ourselves. You don't want to lose that opportunity. It's almost like I don't want to exaggerate, but a moral duty to use the technology in order to solve this problem. I find that really a crucial point, actually.
So do I, but...
Oh, good.
Good. No, we're on the same page here.
Yeah,
the chess example is really interesting because there are two things at issue. One is your explanation of why you made a certain move, yeah, and the other one is how did I come up with that move?
Yeah.
And the how did I come up explanation is close to what we've discussed, explainable AI. But the justification issue is a different one. So it might be the case that somebody, you make a certain move and you say, somebody says, why did you make that move? And then you say, well, look, there's the rook and there's the knight and there's the blah, and you give the whole, you know, so you give an explanation, not in terms of how did I come up with that move, but why is the move justified? And can't we do something like that with AI as well, not knowing how the machine got there, we might still be able to say something about, okay, but now we have a machine that is so reliable I mean, in the sense that it usually gets it right, and then build some other machine that, because what I think that humans do, but I'm not sure if you agree, but what I think humans do in the case of, like in the chess example, is you make a certain move, you haven't got a clue where that move comes from, but then once you look at yourself making that move, you think, that's because I saw that the knight was doing that, and the rook was doing that, and the pawn was doing that. And then you're interpreting yourself, and that self-interpretation, that is your explanation. And can't you do something like that with AI?
So part of explainable AI is to make machines that come up with a story like that.
Okay.
Saying, okay, so it was these data points, it was the head of the bird. That was really crucial for me. When I saw the head, you know, they're not talking like that, of course. That's a typically human talk, but it's the same idea. So it was these data points. So that's the reasons. That's what we humans normally do. But in addition, machines can also say, well, hang on, it was actually the cluster of knowledge representations. You remember the fake thing about the face space that I showed with the eye separation, etc. It was actually that sort of represented knowledge in that particular region of that space that was crucial to making the switch from that particular part of the input to recognizing it such. And if you would have damaged that part, I would no longer be able to classify it as a hummingbird or something. You see? So machines actually provide us with an opportunity to go beyond the standard levels of explanation that humans are able to give. Great, it's technology. We have a right to demand of technology, you know, such increasing levels of accuracy. And in the meantime, remember what I said at the beginning, we use AI also to learn more about ourselves. That's nice. If we can use explainable AI also to increase our understanding, I mean, I also work at the Donders Institute, it's a cognitive neuroscience institute, would be stupid not to use the opportunity. So there are many different reasons. In practice, of course, you can say, look, for self-driving cars, you know, I don't know, 50% less accidents on the road is good enough to accept it in practice. Fine. But making that decision shouldn't legitimize not asking the further questions.
Okay, so there are two parts basically to the explainable AI problem. One is, what about the inputs? Which, I mean, you can have a certain, you can approach the AI system as a black box and see, you know, if with this input you get that kind of output. You compare the two and you see, okay, well, apparently the head of the hummingbird was crucial, or the wing or whatever. So what does that tell us about the importance of the samples that we use in the training of networks.
Yeah, totally. No, I understand. The phrase we always use is garbage in, garbage out. So if you feed a system, a learning system with bad data, out comes rubbish. That's what you're going to get. And in a terrible way, that's actually what we see. So there's a lot of discussions now about biased AI. And of course, people found that a little bit strange in the beginning because AI, computers, you know, they don't have biases. They're machines, they're cold, they just calculate. So how can they be biased? Well, they're biased because we feed them with historical data of biased human beings. So if you tell them to not look at certain types of data, or your database is not representative for a whole population, but has overrepresentative of course, men, 2 men on stage, you know, it's always the same, then you get a learning network that has that bias. So in a way, this is also funny. Technology is always can also be something like a mirror. Eh? If you look at what technology does, you see Homo sapiens in a sort of distorted mirror, and they are just showing us how biased we are. Simply by reproducing bias on the basis of data that we thought was kind of okay-ish. Well, it turns out not to be. The machines show us how biased the data is that we created. So that's another opportunity to learn about ourselves via AI, which I find really important.
Right. But what do you do about that? I mean, what do you...
Well, one thing, I sometimes speak at ministries. I say, I don't understand. I think it's really strange, to say it politely, that you cannot go out on the road with a car in Europe without the car having been checked I don't know how many times. You know, all kinds of quality controls at the factory, at the dealer, and then, you know, you have the APK or whatever it's called. The thing has to be checked every time. And databases, basically anything goes. I can make a database and sell it tomorrow, and nobody checks what kind of data is in there, whether it's representative. So what we need urgently is a kind of trademark quality control, European Union style, for databases. And if you don't have the quality control, you don't get into the market. So Facebook's database should be checked by the European legal institutions. And if they don't want that, well then sorry, no more Facebook in Europe. Which would be a blessing, believe me.
Yeah, I agree with that. But what criteria would you use to
well, I mentioned one. There's many, of course. And it also is tricky because you cannot simply make all the data in the database available because they contain private information.
Exactly.
But it should be possible, completely anonymized, to, for instance, see whether there is an equal, how do you say that, proportion of male versus female persons in a database, or colored versus non-colored. Yep. Or what kind of examples? The earliest databases that were made, they were hand-typed into expert systems in the early 80s. One of the observations was from the computer, almost all humans are famous. Because, of course, what people typed in was everything about movie stars and rock stars, etc. And so the system thought that all humans were famous because well, there's ways of checking such things. And if we don't have the right way yet, then that would be top priority in the research agenda for explainable AI. It's basically, you know, where do you want the research to go to? If this is a serious problem, if we're concerned about algocracy and quality control of AI, well, then fund the research that improves the quality of these machines. Yeah, it's a choice.
Okay. Meanwhile, I'm just saying for the people at home, because we get to the questions in the room in a couple of minutes. But people can use Mentimeter to ask their questions, and there is this code that was on the screen, and I'm not sure it's, but it will probably appear. So if you want to ask a question to Pim, please use Mentimeter. Okay, so meanwhile, do you think this problem is high enough on the agenda of the general audience, of politicians, and if not, what, I mean, this is it's basically a rhetorical question. If not, what do you think needs to be done? Why because I get the impression that people are not really aware of the seriousness of the
No.
problem.
Yeah, no, I think the awareness is definitely growing. And in the zeros, we had sort of the hallelujah feeling about AI. Oh, it was so great. Oh, look at my smartphone. Oh, the things you can do. And then we can, traffic jam problems. We solve them by smartphones because they tell the cars where they are. And everybody was full of optimism. And then in the tens, the last decade, we start seeing the problems and the risks actually a lot more. Remember Cambridge Analytica, the scandal about the American election in 2016, because they manipulated data on the basis of Facebook information. So we're starting to get more worried, but the problem in part, and I totally understand that, is that people think with AI, it's kind of this magic Hollywood ingredient. There's this brilliant system and there's this mad scientist that does crazy things, but it works, etc. Whereas if you look at the system that you try to explain, and I added a little bit, there's actually very concrete questions that you can ask about what does this particular signal mean. And you can tweak it and you can test it. It's science, eh? It's just how we do science. You change a few things and then you see what the results are and you try to build a model of what is happening inside. And so fortunately now with the XI approach, the explainable AI approach, we start putting more effort in that. But the problem is currently, especially from a commercial perspective, there's more money to be made with applications that seem to be doing something useful than with applications that explain how it's done. There's just more economical drive for stuff that does things. The motto of Silicon Valley was always move fast and break things. Because that way you make money.
Yeah.
And so I think it is to governments, European Union level, to make sure that the quality control type of AI that we I think, desperately need is getting very high on the agenda.
Good. Now, I've got a number of questions here now. Just connecting to this one, do you think that AI will be useful in checking AI?
Yes.
Can you explain that? I mean,
well, in a way, I try to explain with a little bit with that the example of the hummingbird and the lesion studies. If you think about it, how many bird species are there? A lot.
Lots. Yeah.
All right. So how many pictures of those do you use in training a network? Millions. How many pixels are there in a picture? Lots. You see the numbers growing? Yeah. Okay. I wouldn't like to hire an assistant to check all these pictures of all the birds for me and do this by hand. That's going to take longer. The sun will be finished before the poor assistant is done. So you need a machine that does at high speed all these checks, and then you have the same with the lesion studies. If you have a network of 100,000 artificial neurons and you want to take them out one by one, that's going to take ages if you really do that with with something technical that I don't know the name of right now. You need to do that computationally. So you need AI to perform those checks about the internal functioning and the inputs.
But would it also be possible to use AI, for instance, to determine whether or not the data set that is used to train the machine is fair? Yeah? Okay. That's also possible.
Yeah, your representatives. There were a couple of students with Tom Heskes from computing science. I happen to be second reader. Great stuff they did on fairness, algorithms to determine fairness. It gets all very complicated and very mathematical very quickly, but in a way, AI can be the doctor of AI in the same way that humans can be the doctors of humans. That's not, I don't see a principal problem there.
Well, the question then obviously would be, who is going to check the checking AI? Shouldn't there always be some sort of human oversight?
Yeah, but it's a different form of AI that you use to check. So they have different features.
Right.
So I don't think that would be a principal problem. It's not a snake biting its own tail. It's not the same AI. It's a different kind of model with different features. Okay. And that should be easily checkable. Right.
Okay, so AI might be the solution to how... We can't trust AI now, but AI might be the solution nevertheless.
Well, yeah, but this is an identity issue. So it's like, which AI are we talking about? There's a lot of AI that you simply can trust. If you use a calculator at home,
It's very trustworthy.
You can trust it. Trust me. You can trust more the AI than me, I'm pretty sure. So there is, it depends, again, and that's also what makes this discussion complicated, like which domains are we talking about? What kind of damage would occur if something would go wrong? How high are the guarantees for appropriate function that we need? It's like, if you talk about an airplane, you check more than if you use a bike. At least my bike in Amsterdam, if that would be an airplane, you wouldn't really use it. So it depends on the territory, the kind of application, and the kind of damage that could be done with the system, what kind of quality controls you can do, and when you think that a certain level of trust is justified.
Right.
And I think that applies to AI too.
Yep. Okay. Got lots of questions,
so
I'll just go on with different questions. There are a couple of really nice ones. Is it feasible that AI could solve a research problem? I would say the answer is just simply yes.
Yes.
Okay.
Already happened.
Then we can go with the second half.
Protein folding.
Yeah, I know.
Last year, because very often AI gets into the news because they become world champion with chess or with Go or with poker or whatever. No, but a very recent protein folding in the three-dimensional, I'm not a biologist, but the three-dimensional structure is really important for the kind of effectivity that it has in a biological system. That was actually solved by an AI deep learning neural network.
Now the question is,
which is a Nobel Prize worthy kind of discovery.
Then the question is, who gets the Nobel Prize? Just to...
Yeah.
That's the question.
Good question. I don't think you should give prizes to machines. It's like, like when Max Verstappen won Formula 1, we didn't give a prize to the car, right? That would be awkward. What's the car going to do with the prize? And it's the same with AI. There's no point in... Okay. I don't praise my refrigerator for keeping my beer cold. That would be a waste of time. I don't punish it if it does something wrong. It's a different ball game, right, with refrigerators. And the smartest neural networks, whether they play chess or do the protein discovery, they're like refrigerators. They're machinery, nothing else.
They don't value Nobel Prizes. That's the
exactly.
problem. That's the
big
problem.
I would think it should go to the team that developed it.
The team, good.
Yeah, the AI people.
Good.
And the biologists, undoubtedly, that were involved there. There's a lot of domain knowledge that you need.
Yeah. So I have a very, very technical question. AI beat a human in the game of Go and greatly influenced opening theory.
Yeah, in chess too.
Yeah. The best was a self-something learning neural network, something technical. Do you think
AlphaGo 0.
Yeah, it says something else here, but okay, yeah. Do you think the theory of Go can change again? Can we completely trust AI in this?
Well, okay, so I'm more of a chess player than a Go player, so I find it a little bit risky to talk about Go, but in chess it absolutely happened. And the story about AlphaGo is maybe interesting. So AlphaGo learned from human feedback. It was a self-learning neural network, but it was still a teacher, and it played games against humans, and it beat the best Go player. 1 year later, there was AlphaGo 0, at least that's the name that I know, and it learned simply by playing against itself. So there was no human feedback anymore involved. AlphaGo 0, so without the human feedback, played against AlphaGo, and it beat AlphaGo with 100 against 0. 100 against 0. And this is something that I find really important, in a way sad, but also liberating. It shows us something about ourselves, about, for me, AI very often tells something about us, which that's why I think it's really interesting. And this is that we pride ourselves, we human beings, Homo sapiens, as being the smartest species on the planet. And nobody, the dolphins don't argue with us, so we can go on believing that that's the case. And so for us, the best human chess players or mathematicians, they're geniuses. So from, 0 to 100 at the level of stupid to very smart, they are at 99.8 or something. But then what these machines show us is that what we think are human geniuses are actually pretty poor compared to what is possible in terms of intelligence. That our best humans are maybe the smartest, of all those creatures with a skull, with the 5-layer neocortex kind of limitation. But the actual intelligence possible in this universe is way much higher. 100 against 0. So we're really very stupid creatures, actually, and all due respect to Einstein, but the guy was a loser. You know, compared to what is really possible in terms of intelligence. And that's on the one hand sad, maybe for us, but on the other hand also liberating. Because if you see the kind of decisions that we tend to make, just look at the last century and a half, you know, there seems to be, it's good there's space for improvement, right? I would think. Yeah. Sorry.
No, I just should say to the people at home, we don't have time to cover all your questions. And now you mentioned this, I'm just dying to ask a question. So sorry, people at home, I've got to ask this one. And then we go to the room. The whole point about human intelligence is that human intelligence is collective. Really, I mean, the whole thing about us being so incredibly smart is not that our brains are so big or that each individual can do so many computations. It's that we're able to learn from each other. Most of what everybody knows is learned from other people. There's hardly anything you've thought up yourself, but what we know is incredible because it's collective. There is nobody on earth who understands how an iPhone works. There's just nobody does it. It's the collective that can build iPhones.
I think Steve Jobs was
he was probably quite far advanced, but there are details that even he doesn't know. And it's the division of labor that makes us intelligent. Yeah. That is what makes human intelligence really. It's not the individual chess player, it's the community that does it. And now the question is, can you envisage something like that going on with AIs? Is it possible that AIs start learning from each other, form networks? Like, I mean, we're intelligent because we're communities.
Oh, yes. So maybe it's not a good example because people think of it as a very bad thing. But you know deep fakes? You know, the fake pictures and or the movie clips where Nixon suddenly starts doing a speech or Obama starts singing, etc. You know, deep fakes. That's actually created by 2 deep learning neural networks that fight against each other. Mm. So one creates, on the basis of data, a fake picture, let's say. I have some wonderful pictures of people with fish that they caught. And this network tries to make fake images of real-looking but not real people with fish that looks like real fish, but they're not, you know, actual pictures of fish. And in the beginning, of course, that network is really bad. So there's another network, a deep learning network, that is the judge. And the task of that second network is to discover whether it's a fake or a real picture. And these sort of fight against each other and become better in the process, so that ultimately you get pictures that are so realistic that for us, at least, there's no point in discussing anymore because we can't see it. So that's actually, we call that GANs, doesn't matter what it stands for, but that sounds like one AI, but it isn't. It's actually 2 modules that work against each other. Mm. So yeah, is that learning from each other?
Not really, but it's the first step. I would think.
Okay.
It's not like cultural learning in
no, the mechanisms could be different, but I wouldn't know why you couldn't write programs that write programs, for instance. I think they are existent.
Okay. Interesting, scary stuff as well. I would.
But the thing, sorry, in terms of scariness, I don't think we should be afraid of machines that start to grasp power and do what they want, because there's no wanting.
There's no wanting. Yeah.
There's a stupid usage by us of smart machines that makes me scared. But this Hollywood scenario of a machine that suddenly wakes up and thinks, you know, I'm done with cooling beer. I'm gonna, you know, bake a pie or something. I want to be an oven. You know, no, it's not going to happen. We don't know how to build wills. We are capable of building machines that are really intelligent in certain domains, and we can do very damaging things with that, and we're already doing. But building a will is something else.
So thank you very much. No, we're way over time. So thanks, Pim. Thanks a lot for a talk and for the discussion. Thank you for being here. This is I don't know if this is the first live event that we had, but anyway, it was really nice to have people present and that you can actually talk to and look in the eye more or less. So thank you very, very much for being here. Thank you everybody at home for watching this program. Do check out our website for there's lots of very interesting other programs coming up soon. So thank you for joining us. Bye-bye. Thank you. Thank you.